Before we get to condensation, we're going to do a quick ketone aldol reaction. Same thing as aldehyde, only ketones don't work that well. We're only going to get really like 1% of our product. Let's just do a there. Same again, OH minus. We need an alpha proton. I wonder, do we get? We're going to find out. I didn't even think of this. So I have an option of either taking an alpha proton on the right or the left side. We're going to find out if we get different products for that. So let's go ahead and take it first an alpha proton, and let's do this in red. Now, yeah, red. Let's choose this alpha proton and see what we get. Enolate anion. And this is a little, I'm not giving another ketone there, so it'll react with itself. Who has electrons, who wants them? Push that up onto oxygen. Okay, let me draw this here. We pushed bond up onto oxygen. And to make a little bit of room, I'm going to put this methyl group straight down for now. And, okay, here's my enolate. There's my enolate carbon, and on that carbon I have 1, 2, 3, my ketone goes there. So I've added in the beta position, that looks good. And then I would use water here to protonate. I didn't draw that in, but you should. Let's go ahead and now take an alpha proton on the right side of our ketone, and this one will be green. Okay. Work down here with it. So, as electrons, oxygen will take this here and we'll form an enolate there. Plus another one. Okay. Oops. Push that bond up onto oxygen. Again, going to make a little bit of room to add stuff on, so I'm going to take this methyl group straight down. I have an enolate anion right there. Okay. And then on that enolate, I have a methyl group to the right. There's the methyl group, and on the left side, I have 2 carbons, 1, 2, and my ketone right there. All right. Yeah, I formed 2 different things. Isn't that nice? Okay. I don't know if your book even addresses that. I mean, maybe it does. Man, does it? You know, I don't even know if it addresses that. It also uses a symmetrical ketone. So I use an asymmetrical ketone. So that's something to keep in mind. That's odd they don't do that. Now, is one more acidic than the other in this case? There's not really much. I mean, I would think maybe the one on the left is very slightly more acidic, but that's tough. So I think there are 2 options for that. There wouldn't be in a symmetrical ketone, but it's a good question to ask Dr. Andrews, and I will do that. But in the meantime, I don't see any reason why we can't take alpha hydrogens from either spot there. So Yes, you can do ketones for aldol reactions, but again, you're only going to really get 1% of your products down here, and I'll protonate that. And you're going to leave yourself with like 99% of your original ketone. That has to do with, first off, steric strain with this carbon here, this carbon here. It also has to deal with, notice that I started with 2 carbon-oxygen double bonds, which are high bond energy. Okay, so strong bond energy, and I only have 1 in my product. Here I had 2, I have 1 in my product. And then the last thing was ketones don't make very good, especially with, I mean, we have a large ketones. We have, compared to aldehydes, more steric hindrance here with our large nucleophile attacking a more crowded area there. And one more thing, from chapter 18, remember ketones are not as fast with nucleophilic addition because they have 2 alkyl groups contributing electronegative charge to an area that we want a partial positive, our carbonyl. All right? So a lot of reasons why we only really get 1% of this. If we want more in our solution in our product, we can take out what we've made to have an equilibrium shift. Even if it's like 1%, to maintain that, we can take some of our product out. And yeah. Okay. I'll ask Dr. Andrews about that if you have 2 options of an alpha proton, but I don't see why not. We wouldn't get 2 different reactions there. Now we're going to do a little condensation and we'll be done. Happy Saturday. All right. Here are our products from our last video from our aldol reactions. We're going to go ahead and do a condensation, so it means we're forming water. At some point we should form water. And we're going to perform condensation reactions. We should expect there to be conjugated conjugated double bonds here, not dienes necessarily. Basically, our OH groups are going to leave and we're going to form a double bond there. That's it. To do that, we're going to use, again, OH minus, just like we did when we formed our aldols. And we'll have water and heat. Heat is our major, I'm not so sure the water is even necessary here. Heat is definitely need heat. That's going to be our major difference. So we just use OH, perform our aldol reaction, we continue with OH, we heat it up though, and now we're going to have a condensation reaction. Let's go ahead and start out with that top one. And I have OH minus. Who has electrons and who wants them? No, it's not that. It's going to be a, change the color. We're not going to go straight nucleophilic attack in this case. We have heat, so that's going to favor elimination. Elimination, think alpha proton, we're going to do a base reaction. Heat is telling us that. Without heat, I think this would probably be a nucleophilic addition of some kind. With heat, elimination. It's always going to be between my 2 groups. I'm going to take an alpha proton in between them. Form a enolate. Is this different steps? I gotta make sure. Okay, perfect. Okay, yep. They form an enolate first. Okay, this next step, stupid. I hate it. This whole time we've been telling you that OH is a bad leaving group, and it is. Now we're finally going to break that. This is going to be the exception. It's stupid. It's dumb. Okay? Yep. Double bond, OH leaves. So we had OH minus in solution. We're not going to really protonate this in basic conditions. It's just going to leave. Your book talks about it a little bit. The E1-CB mechanism might at first seem to contradict the general rule we encountered for elimination reactions in section 9.9, which states that OH minus leaving group is generally unsuitable for E1 and E2 reactions. An E1-CB mechanism is not strictly an E1 or E2 mechanism, however, so the general rule is not broken. It doesn't explain anything, really. It doesn't explain why. Moreover, the poor leaving group ability of OH minus is partly compensated for by the stability that arises from the conjugation between the CC double bond and CO double bonds of the overall product. Meaning, when that leaves, we get conjugation, alternating double bonds, and OH minus. It's stupid, breaks the rule that we've been following the whole time, but OH minus will be our leading group. Not really many steps. I can see this being, I can actually see any of these reactions being in a synthesis problem. It's tough to find out which one's going to be in it. I wish I knew. So go ahead, try one of these at least. Not all three. You should try all three, but whatever. Condensation reactions to get these. The reactions aren't that bad. It's important to remember though, in condensation of aldols, OH minus is a leading group. So I'm going to go through these kind of quickly. I'm just going to do, I won't do all of them. You can do them if you want. You should expect there in the product to be a double bonded CO, and then it will be conjugated with a CC double bond. Let's go ahead and do this one. So we're going to add, what are we going to add? OH minus, water, heat. Remember OH minus, basic conditions, alpha proton first, enolate anion, okay, negative charge there. OH minus is a suitable leaving group in this case. Let me go ahead, push it off, make that double bond, and that's it. OH minus. This OH minus can go over here and react with this one. We get a conjugated product with that as well. Where did we make water in our condensation reaction? Right here. We had OH minus accept a proton, and we made H2O. There's our condensation part. All right, that takes us most of the way through chapter 19. Well, barely most of the way. This is just going to have to require a lot of studying. There's no other way to put it. No other way to put it. Hopefully these videos help. Go through practice problems in the book. It's going to take some time, but might as well invest all that time now rather than in a retake and another retake. So recommend putting in the time now. Watch these videos, work with someone else. If you can, design your own problems. That's the best. And hopefully these rules that I've made in these videos will help make sense of this chapter 19, which is, I would admit, pretty dense, pretty rough. So Monday and Tuesday SI sessions as well. We'll go over anything you guys want, and we'll certainly be over the 50 minutes. Yeah. All right, well, that's gonna do it. I will see you all Monday and Tuesday.